Okay, good evening, everybody. The couple people that are in here already. Going up, 5 o'clock again. We'll get started here. What I want to do today is talk about a couple drawings I made when I was in school. So these are not going to be very good technically, but if you're a student, it might be something like what you have going on, right? So this is the main one we'll talk about, and I'll talk about these two little gears as well. And if we have time, I've got one other drawing that I kind of found laying around the college, and we'll discuss this. It seems like I got some, you guys like it when I talk about drawings, so I think it's a good way to learn, right? This is how you learn, is you make a drawing and you get corrections on it. Okay, so let's get Pepper. Get out of here. Scram. Okay, so let's get started. This, as you could probably tell, is a gear, right? In CAD, modern CAD systems, you can leave gear teeth. It's fine. I'd almost not recommend it though, because it clutters up the drawing, in this view especially. What they used to do when you had gears was just use kind of like a like you would do on a thread, is you just use a hidden line to indicate the minor and major of the gear, and that way you clean up the drawing. This is fine kind of here, but say if this view, if you're using it in assembly and it gets real small, you end up, right, it would just look like this, right? It would be all lines smushed together. So I would recommend, and I didn't do it here when I was a student because I didn't know how. I would recommend going in, maybe try to figure out how to, remove the gear teeth and just show one. But really, this is the information you need for a gear tooth. Like the machine shop isn't going to like put a ruler on this and measure the gear tooth. They're just going to go off of whatever data you put on the sheet there. Okay. So with the gear, right, I would say 9 times out of 10, right, we want it to spin about its axis. In this case, it's just a single gear, not like 2 gears smushed together or anything. So we've essentially got about two features that could be an axis for this. And what I mean is, we've got this diameter, this 0.53, that could conceivably give us an axis that's coaxial with this axis here. And again, I was a student, this says radius 0.063. Well, why does it say radius? The reason, Pepper, you are all in the shot, aren't you? Let's be a good kitty. All right, so the reason it says radius is because a CAD program doesn't know anything, right? I know now that that's a diameter, right? This feature should be a diameter or something, and it just happens to have a flat on it. But a CAD program doesn't know that, so you need to go in there and manually change it to a diameter. Radius is only typically used for things that are less than 180 degrees, and this is, more than 180 degrees of a circle here. So, you could say it's minor, but that will raise eyebrows if you send this drawing off to get quoted or something. People are going to look at it and think, wait, why isn't that a diameter? Like, is something else going on? So it should be a diameter. Okay, so what I'm getting at is I can make this feature, we'll call datum A the primary, or I could use this feature and make that the primary. I would go ahead and say that you want it to be this internal feature, even though it's smaller and slightly more difficult to get at. That's going to be the functional feature there. A machine shop or whatever would prefer this one because they can grab it from the outside, which is convenient. But this could come out, right? This feature right here, this 0.53, could be all out of whack, and the part could function just fine, right? It's just kind of an extension. Maybe it's used in the, you're not going near the keyboard. Maybe it's used in the manufacturing process or something. So I want to bring that up because you got to be able to explain these decisions to people, right? What sets the orientation of the part in space? It's this thing that a shaft is fitting on, not this larger cylinder that is just mating to air. Okay. Another little drafting problem here is this has the width of the flat dimension. You typically want to avoid this because it's difficult to measure. The way you'd probably want to do this kind of half round feature is you'd put the dimension like this. That way you can just measure from one side to the other. It's the same way you would do a, what do you call it? When you have one of these, right? You would prefer to measure it like this, right? From the bottom of the slot to the other side. It sets it so you're measuring real things. You could say this is a real thing, but it's difficult to ascertain where this edge is. And this dimension right here would set that width. So just a little minor thing. You would find the drafting information for this feature with what do you call it? I forgot what that feature is called. It would be this. So keyway, that's the word I'm looking for. So this is the preferred, and this is from like 1950 something, but trust me, it hasn't changed. This is a preferred way to do it, from the opposite side to the landing there. What we're looking at in our little example drawing that I'm going over on the other screen is just this situation, except it's flat straight across. There's no edge here, right? So same idea. Okay. So the book I'm looking at is Military Standard Dimensioning and Tolerancing, Mil Standard 8C. I got this off of eBay. If anybody knows where I can find any of the other versions, please let me know. This is a pretty short little book. It's probably like 50 pages. And it's just GD&T before GD&T. Okay, so we would make this a diameter, and let me make sure I get this number right. It's going to be about 0.126, 0.125, whatever. Every spec free download. For real? Huh. Is that really a free download from, what did you say, every spec for that? I'm looking at the chat if anybody's wondering. Okay, so back to here. I want to stay on track. This is a little bit tricky of a situation. We would need to probably call this out as a basic dimension, because you could sort of call it out as a plus minus diameter. I'm a little torn on how you would want to do that. Basically, the way they're going to inspect this is they need to take like a collet or whatever, an expanding collet, and nip some of it off. So you could say this is a what do you call it? Basic, and just give it profile of a surface of, I don't know, something. And then, oh, I didn't put a little step in there. And then all around. And that essentially give it like, I don't know, plus or minus 0.03 essentially for that feature. So when you're using it as a datum, right, you're just expanding to capture it. So, you know, there's ways to do that. It's not the end of the world. Okay, so we'd establish this, right, as our datum A. Datum B could be what I had spec'd as datum A on this. It could be either one, right? We can make that datum B, or we can make that datum B. I probably lean toward the side with the gear on it, just because there's more stuff going on there. You could probably get some added benefit from that being the datum face, because it's going to be touching the gear teeth there. Also in this drawing, the dimensions are originating from there, so it makes things a little bit easier. Okay, so we would go basic, basic, basic. This diameter here, because it has a flat, we'd actually probably go, well, I don't know, let's not go basic on that one. I want to talk about something else. This flat, again, like I said, I wouldn't dimension it like that. We really need another view to show what I'm talking about is this feature. It's kind of barely visible on the back side and here. We really want another view for that. But what I'm getting at is because there's a flat, right, this spot right here, you would like to apply a run out to it because it's a part that spins. That'd be convenient. In 2009 and previous, in 1994, 1982, 1973, and before, you couldn't apply a run out to something that wasn't fully round. So what I mean is, if something has a flat on it, right, the needle is going to drop with your run out and it's going to fail. So a lot of times you'd see a part like this, right, where you have a cylinder with a flat, and they'd apply profile to it, just like I did over here, for that reason, even though it's a part that spins. In 2018, it's pretty cool. They actually got rid of that. So they said, hey, obviously I don't remember the exact wording, but basically you can apply run out to something that has surface interruptions as long as the part, I don't know, that's supposed to be round, the run out applies to that. It doesn't apply to the flats. So that being said, I'd consider applying run out to here. And this is a horrible way to do it, right? You typically don't want to apply something to where it's only halfway visible. So what I mean is this cylinder, let me mark it in red. This cylinder is visible over here, but it's really not a great way to dimension stuff. You'd really want another view of the whatever. This is front, top, and you would want the bottom view of that. Okay. So we got basic dimensions. We would do profiles for all of these surfaces. I'd get rid of this parallelism. Datum B here, I would just say, hey, it's going to be a profile of something to datum A. That means the same thing as saying, hey, it's perpendicular something to datum A. Same meaning. Then these surfaces, right, the backside of this, right, we just come in with a profile of something to A and B. That's going to lock all those in. For this hole that's not coaxial with datum A, we're going to apply a position to that. And that really shouldn't be a problem at all. Just slap a position on it. You don't have to change the datum reference frame, and that throws people for a loop sometimes. So here's where the position would go. Diameter, something, something, A, B. It doesn't matter that this hole is not coaxial with A. You don't have to do B, A, or anything, just A, B. The origin for the datum reference frame is over here. It's fine. It's all going to be located with basic dimensions, so it'll work out. Let's see, what else do we have going on here? I think that's about it. It's not a very complicated part. And, this is like a school project. A lot of times gears are available by catalog. So I think this is something that was just like downloaded from McMaster-Carr and then maybe dimensioned, but outside of school, it really doesn't need to be. You wouldn't dimension something that you could just buy. Okay. Here's another one. I don't think there's going to be anything really special about this where I'd want to spend any time on it. Basically the same kind of thing going on. Okay, let's take a look at this. Oop. This is a little bit more complicated of a part. We've got a little box, right? And the idea of this, or I call it a motor mount, I guess, is that a little electric motor fits in there somehow. I think it fits in kind of like this, right? There'd be like a shaft somewhere. And then there's some gears, like the gears we were just looking at, that fit in here. And the idea with these little bosses is a little bearing fits in there. So there's like a little shaft that goes across each of these with a little gear in there that, you know, spins or whatever. So let's take a look. Let's find our datum feature symbols. All right, so we got A, B, and C. So based on this, right, datum A is this bottom of the part. That makes sense. And I even had the foresight to put a flatness on it, right? Even though probably back then I didn't really know why. I just knew that people did that. Datum B is going to be, and let me use a different color here, this backside of the part, right, over here. And I did not have the foresight, right? This should have some kind of orientation tolerance back to datum A. And that's a fundamental thing, really can't get around. So we'll add that in. And then datum C is a little weird, right? I've specified it, let me use a different color, as being like the edge of one of these bosses. But what that has the effect of doing is putting our coordinate system like out there in space, which is certainly not ideal. But that's essentially where our coordinate system would be, kind of the corner of the part, but pushed out into space a little bit because of, you know, this boss feature. I would definitely not do datum C like I did here. I don't think it makes any sense. That's not a functional feature there. It's not really going to limit anything in space. That doesn't fit up against anything. What we'd probably want to do here for datum C is choose like a big surface of the part and not this little dinky boss. Or even consider, since this thing is symmetric, we might want to come in this 1.5 inch, right, and center that dimension. I think making that mid-plane would probably make the most sense. Then that would indicate to anybody dealing with this part that one side doesn't matter more than the other. It could cause some minor inspection headaches, but you know, the design intent is that, hey, this is a symmetric part, making the center of the part datum plane C really gets that across. Okay, so we've gotten rid of, or we moved datum C, and so let's, we would want to qualify this, so we could use a perpendicularity here to A and B, and then we'd be all set, right? That would be a fully, you know, defined datum reference frame. And from there, we would build out everything else. So let's look for some mistakes here. I'm not sure what's going on here, right? This is, I'm sure those of you that use SolidWorks know yellow means bad. I'm sure it's the same with all CAD programs. But Yellow is going to indicate that there's some breakage between the model and the drawing, so there's just stuff missing, so I'm not going to worry about that. Well, when we go to a datum reference frame here, our dimensions have a little bit more leeway in that they're basic and they don't stack up. So some of these, right, we're just going to make basic. I think in the drawing here, I had the idea that only the things locating position needed to be basic, but of course now I know that's not really true. If we use profile, almost anything could be basic. So let's take a look. We've got this position here, 2 times 0.435. Pretty sure, yeah, it's going to apply to number 1 here, number 2 here. So we've got the position symbol, diameter symbol, some value. In this case, it applies at maximum material condition. And we're going to A, B, and C. Now, the only other thing we could do here, since we made datum C a feature of size, we could have datum C apply at maximum material condition. Otherwise, this is basically fine. What we don't need a leader for this position, right? We could just attach it to this dimension, and that's the way it should be shown. Position can have a leader in ASME. There's very few reasons why you'd ever do it, because it's almost always going to be associated with a feature of size dimension. Okay, same idea over here, right? We get rid of this leader for this position. That's not going to be necessary. And then we've got the same tolerance. Not really sure where that came from. Again, we could make this apply at maximum material condition, which may be helpful. So what I would do here, I would just make basically everything basic and control a lot of this with profile. And I'm saying that is the way the 2018 standard really emphasizes. And I think it makes sense in a lot of situations. It just kind of simplifies things, in my opinion, and that you don't have all this tolerance stack up locating things. So I did get a question here. Why not use position for the datum C feature instead of perpendicularity? It doesn't need position. Let me try to explain this with a over here. So say we're going to set up a datum reference frame, right? We're going to have Z coming out of the table, X and Y. Say this little granite plate here is datum A. We're going to apply a flatness to that. And we're going to say this book here is datum B, right? The book just needs to be 90 degrees to datum A, right? It's 90 degrees, but it can still, rotate, right? Even if it's directly 90 degrees to the plate. You can kind of imagine that, right, as being propped up by this block, but it's still allowed to spin, right? So that's why we can use perpendicularity with the secondary datum. Now, where the tertiary datum comes into play, let's say we add another book here. I'm sorry, these books are bigger than I thought. Right. If both books are 90 degrees to the table, it's still not enough. They need to be 90 degrees to each other. Right. So whether they're 90 degrees to each other at this corner, or as in the case of a center plane, they're 90 degrees to each other like this, right? They've still got to be that 90 degrees. So that's why it's to datums A and B, and you end up with something like this, right? Where you've got this one's 90 degrees to the table, this one's 90 degrees table, and 90 degrees to this. Hopefully that answered your question. Also, you could use position. I probably wouldn't recommend it because I don't know, it could cause more questions than it answers, but it would just be kind of, I don't know, over defining it. It's kind of like using position, but not all the position features get utilized. I would say to use perpendicularity there. Okay, so another question is, the position tolerance can be used for plane to datum measurement? No. So in ASME, we have to use profile if we're locating planes to datums. Position can locate a center plane, but that's a little bit different. That's from a feature of size. It's kind of like locating the axis of a cylinder. But if you're just looking to control the location of a plane or like a curved surface in space, you will have to use profile with ASME. And ISO, you can use position to control surfaces, not a problem. Okay. Let's see, was there anything else on this one? I guess this part is a little bit simpler than I remember here. Okay. All right, so I hate to tease this, but I'm gonna make this live stream a little bit shorter than I want to keep them around 30 minutes. I'm gonna save this one for next time. I think this is going to take a lot of time to cover because we've got a lot of different features. And I'll stick around for a couple minutes if anybody has any questions. It's in the chat. I think there's like a 30-second delay, so you know, if you see me like staring off into space and not answering your question, that's why I don't see it for like 30 seconds after you send it in. So feel free to send a few, and you know, if you have anything in. And if not, I'll be getting out of here, you know, pretty soon, and then I'll do this again next week at the same time, and we'll cover this drawing behind me. Yeah, if you have any ideas, feel free to you know, put them in the chat or put them in the comments when the video's over. That's helpful as well. Drawing from Drake book 5-127. So the drawing, page 5-127. Okay, so I don't know if I've ever seen this drawing before. Let's oh, 5-137. Oh, this is a fun one. Okay, I do remember this one. Okay. So we've got a triple composite position. Let me see if I can kind of break this down live. All right. So with composite position, or composite, however you say it, this top one is going to control the pattern and the feature-to-feature relationship. So translation and rotation to the datum reference frame, right? So the translation is the distance, right? This point, or 6.209. Figure 127. Yeah. Uh, and that's pretty straightforward, right? So we're measuring how far those two holes are from there, and then we're controlling atoms B and C are a little funny because it looks like they're okay, they're both planes. Okay, I see. So you're basically getting an axis out of that. Now, where this one is a little weird is now you're controlling just the feature to feature basic relationship. And maybe this is where it gets a little confusing. There's basically a zero basic dimension between these two features, right? And that's what keeps them coaxial. So we're always, even if there's no datum there, we're saying, hey, the coaxiality is 0, and then in this case 0.02 is kind of the limit on that, and that's kind of unsaid in ASME. Now the second one, we're just controlling rotational degrees of freedom and that feature to feature basic relationship with the second one. So what are we to A? We're parallel to A, right? That's the rotational degree of freedom. So what it's trying to tell you is that we're allowing, we're controlling how parallel this is to A, right? And controlling to a lesser degree, and I can't really draw this, the rotation in plane, right? So it can twist relative to C and B, but not to A. It's important for this designer that A is parallel, or these two holes are parallel to A as a pattern. I don't want to write in my nice Drake book here, but essentially you would have a 20,000 cylinder going all the way across to A, B, and C, a 5,000 cylinder that's free to do anything except rotate relative to A. So it could go to the top, bottom, left, right within this 20,000ths. And then the last one, which I think is what probably throws most people for a loop, position without a datum reference, like that's not allowed. It technically is allowed. There's one exception, and the exception is coaxial cylinder stuff. I think I made a video about this one time. But basically it's saying, hey, this only controls the coaxiality of those two holes relative to nothing. So we've got an even smaller tolerance zone just for those two holes. So that's to control the fit. So if I go to slide something in here, right, I know we're good within 2,000ths. But the gross position of the pattern is larger than that. Yeah, and that's how to explain it. Hopefully that helped you there. And yeah, this is, I really thought about it. Yeah, if you have figures from, some of you know what kind of books I have laying around from the last video. I can't recommend this one enough. The downside to this book is that it's to the 1994 standard, so there are some inconsistencies. You kind of got to be hip to 2009 and 2018, but the breadth of information is just amazing in this book. All sorts of handy stuff. And I got one more here. Could we discuss a pattern of holes as a datum in the future? Let's say a block of 4 position holes in the corners using profile to tolerance the outside perimeter. Yeah, we could touch on that now, I think. So let me switch here. So let me kind of enter the void here. All I can really do is a super simple explanation for you right now, but a common situation, right? So we have this little part with 4 holes, and let's give it another view. All right, we got a little view down here. And why would we want to make, right, these holes a datum, right? What would possess us to make things more complicated than they need to be? Well, it comes up, say these 4 holes, right, you have fasteners or something going through it, and the outside of the part just mates to air, like a light switch cover, right? Only the 2 holes really matter, and everything else doesn't matter hardly at all. So in that case, it wouldn't make sense to make these edges datums, right? Because they don't mate to anything. If there's just air out here, we don't need to be measuring from them. So what we want to do is measure from the things that actually matter. So let me draw a picture, right? Here's a light switch cover. I'm sure most people know what I'm talking about, right? With a light switch cover, these two holes matter. The outside could literally be anything. Well, not anything, but it'd still work, right, as a light switch cover. I'm trying to get the name right. Mr. Siafi Kamazan. Book reference, check the last video. I went through like a bunch of different books. The last live stream from last week, I went through 6 or 7. I don't know if that's the exact number. I went through a bunch of books and went through the pages and talked about references and stuff. Okay, so in this situation, right, we're gonna let me get a different color. We're gonna make one of the planes datum A. That's pretty typical. We'll come in here, right? We've got 4 holes with some diameter. Now we've got to use position here. Why do we have to use position? Why can't we just use perpendicularity, right? And that's going to come up, and I bring it up because people are going to ask you and you'll have to explain yourself. The reason we have to use position is we're going to have a basic dimension between these holes. Right? Perpendicularity only controls individual features. So if I said, instead of position here, if I said, hey, perpendicularity, all of this basic dimension with the holes doesn't matter, right? Because perpendicularity has no effect on that, right? It's just each hole needs to be perpendicular, but it could be anywhere, right? It's typically controlled locationally with plus or minus dimensions, but we don't have those here. We have basic dimensions. So we've got to use position, right? Position is going to control the feature-to-feature relationship, right? That basic dimension from one hole to the other. That's why we use it. And then datum A controls the perpendicularity. So position does 2 things. Perpendicularity only does that one thing. Okay. So what we're saying is, hey, by the way, this pattern of holes serves as datum B. Now, the next thing, right, we do all that cool stuff. We got to use it for something. Typically, it's going to be a profile. I'm just going to do, nothing for now. We're going to do A, and I'm just going to tell you, you should use MMB right here. Why use MMB? Doesn't that make things more complicated, difficult to understand? People are going to raise prices on me. They're going to freak out and overquote it, whatever. What you're asking for, if you send this as RMB, regardless of material boundary, right? You've got a pattern of features of size. What that means is that when you simulate it, you have to have 4 perfect, true geometric counterparts, right? They're they're perpendicular to datum A, and they all expand simultaneously, perfectly, until the part is captured, right? So imagine 4 expanding pins that expand until the part fits, and then you take your measurements from the center of that. It's very difficult to do practically. There's some examples in ASME Y14.43. It's like the gauging standard. They actually have pictures of some device they draw that could conceivably do something like this. I can tell you it looks very expensive. What calling this out at MMB does is notionally allow you to drop it on 4 pins, right? And you might say, okay, well, I'm just going to check it on a CMM, so who cares anyway? Well, you could still use the pins with the CMM, right? So the idea is you make this thing with 4 pins, right? And you put it on your CMM table and you find the 0, Now you can just drop a part in there, right? And then just measure each part. You don't really have to do an alignment every time. So it can still have advantages. Also, CMM software wise, you got to be careful with the fitting algorithm if you're going to be using stuff, patterns and features the size at RMB. You kind of have to know what it's doing behind the scenes. What was the other thing I want to mention about this? Oh, the where's 0? It's typically in the middle of the pattern. You can move it if you want, because they're all basic dimensions. It doesn't really matter. So if you wanted them all to come from this hole, I can't think of how to do it right this second, but there's ways to kind of move the 0 around. But yeah, typically it's going to be right center of the part. So you could think of it as a center plane and a center plane, however you want, but that's where your measurements will come from. And that's why these basic dimensions are centered on that feature. Even though you're not calling out a feature of size as a center plane datum, that's what it has the effect of doing. You get an axis, it's the same thing as two center planes crossing. Oh, I don't know if I can do this question now. If a datum surface is suspected defective, what is the process for changing a datum choice for CMM alignment? That's a tough question philosophically. I would say you can't change what datum you're going to pick. And so I'll just draw like the simplest possible case, right? We've got a block, and maybe we have like a couple holes. Datum A is here, and the designer, and I know this isn't going to be what you have going on, but maybe it's vague enough, right? So say we've got a position for these holes, right? And please don't screenshot this drawing. This looks terrible. Position to A, and we're saying, geez, we're getting this part in, and A is just wrecked, right? It's for whatever reason, it just sucks. Maybe it's just convex and it's rocking. We can't move it over here, right? Because this is what the designer, and I know this part looks symmetric, but say they, I don't know, put like an ident mark here, right? This side up, right? Whatever it is. I would assume you would need some kind of paperwork to move the datum. That would be my opinion. I wouldn't move it unless I had some kind of written, express, CYA documentation for that. Okay, hopefully that helped. Okay, guys, I'm gonna get out of here in just a couple minutes. Those are really great questions. We got another 15 minutes out of that, so I enjoyed answering those. Those were good as always. So I'm going to give it about 1 more minute, and I'm going to go ahead and log off. Again, if you have more questions, please put them in the comment after the video ends. So I don't know if you know this, that the comments or what you put in the live chat just like goes off into the void when the video is like done and posted. But if you go and comment after the live stream is done, that sticks around forever, and I can see it and kind of get it into the system and maybe start a video with those answers. Cool. Okay, guys, I'm gonna go ahead and log off here. Thanks for joining again, and I will see you next week. I'll try to do this again Monday at 5 p.m. Eastern Standard Time.